talk about lava planets. Please stop me if I say things that you don't understand. Like those kinds of clarification questions, just yell them out. Because this is the first time I give this particular talk, especially to such an interdisciplinary audience. Okay, everything I'm going to present today is stuff done by other people, usually people in my group. My group, as you can tell from the logo, usually uses space telescopes to characterize exoplanets. Today I'm going to show you precious few real data, and that's because we are still in the process of analyzing the very first observations of lava planets with the James Webb Space Telescope. So that's something that's going to come out in future months. Right now we're still kind of scratching our heads. So mostly what I'm going to show you today is theory work that we've been working on. So without further ado, let's introduce the main event. So lava planets. These are very simple. It's just a rocky planet, so something like made out of the same stuff as the Earth, rock, iron in the middle maybe, and you heat it up enough that you melt the rock. Okay? So to be clear, all rocky planets, including the Earth, started molten. They all start hot. But then in normal planets, they cool off pretty quickly and get a solid surface, as happened on Earth. But lava planets are orbiting so close to their star that they're so hot that at least one side is permanently molten. Okay? And hence, it's lava. It's like magma at the surface. It's lava. And so, astronomers are not terribly creative with names of things, so we just call them lava planets. We know of a handful of these. Okay? So this is a plot of the mass of the planet is your x-axis, and the y-axis is the radius of the planet. Okay, so this is the so-called mass-radius diagram. The colored dots on the bottom, those are the ones that are kind of the smallest for a given mass, either the highest density. Those ones are all consistent with an Earth-like composition. So the colored dots there that have names next to them, the names are horrible. They're all TOI something. That means it's a TESS object of interest. These are objects found by the TESS satellite. This is a NASA kind of planet hunting satellite. And those colored ones at the bottom are all high density. They're made out of the same kind of stuff as the Earth. And the color is telling you their dayside temperature. And it's really hot. In all cases, it's above the melting point of silicate. So in other words, rocks will melt. So you'll have at the very least, a puddle of magma on the dayside of these things, or maybe an ocean. So we can find these, and we can actually try and characterize their atmospheres. And so this is what we're trying to do now with the James Webb Space Telescope. But what I'm going to talk about today is more kind of the theory of how these planets might work, because it's quite weird. And I'm sort of going to cast this as a bunch of questions. The first one is super easy. Do lava planets have an atmosphere? Who here thinks they know whether a lava planet has an atmosphere? Just like a raise of hands. You think they have an atmosphere? Yes. Who thinks they don't have an atmosphere? Wow, it's pretty evenly split. All right, well, let's talk this through. So we know by definition, a lava planet has a magma ocean, right? I mean, that was the definition. I told you that they're made out of rock, and I told you they're hot enough to melt rock, so they've got molten rock on them. Okay? So in my cartoon here, that's the yellow stuff on the left. That's your magma ocean. Turns out you can't have a liquid and then vacuum. If you have a liquid, there will always be some gas next to it, right? This is like saturation vapor pressure stuff, which means that by definition, a lava planet must have an atmosphere. It could be a really thin atmosphere, but it's got to have some pressure, some atmospheric pressure, and it's vaporized rock. It's made out of basically the same stuff as the ocean. So from the moment these planets were discovered, we basically knew that they were going to have an atmosphere, and then you can try and guesstimate what that atmosphere is. The hardest part is knowing what the planet is made out of. Of course, I say they're all consistent with being made out of the same stuff as the Earth, but that's like a very vague statement. There's different kinds of rocky planets that might have slightly different mineralogy, and that would lead to slightly different atmospheres. But as an astronomer, I can take the really big picture view and say, it's vaporized rock. Okay, and then the geologists are like, oh God, that's so dumb. But it's okay, that's what I'll say. So it's basically vaporized rock. And then I'll get into a little bit more detail about what that is later, but not much more detail. Okay, so on the day side, yes, there's an atmosphere. So these planets for sure have an atmosphere. On the night side, probably not. Because these planets are orbiting so close to their star, right? I guess I haven't told you just how close they are. They're very close. So to scale, if this is a star, the lava planet would be about 2 stellar radii. It would be about there to scale, which means if you're on that planet, your star, instead of being like an Advil held at arm's length, would be a yoga ball held at arm's length. So your star is just like fills up a large fraction of your sky. Okay, so it's very hot. To put that in orbital parameters, we're talking like, I don't even know what that is in astronomical units, because that's a dumb unit when the distances are so small, but it's like a 6-hour orbital period. Okay, so you're flying through the corona of your star. Like that's where you live, is in the corona. Like the thing you will all see when the eclipse happens. Hopefully you'll see it if it's not cloudy. Imagine a planet that was flying through that weird plasma stuff. Okay, so the point is when you're that close to a star, your planet is going to be tidally locked. Okay, that means it's going to have a permanent day side, permanent night side. On the permanent night side, you haven't seen the light of day in billions of years for the entire existence of your solar system, basically, which means it could actually be really cold, like colder than the surface of the Earth, like 100 Kelvin, 50 Kelvin temperatures on the night side. So that means you got an atmosphere on one side, no atmosphere on the other side. And so what that leads to is winds, very, very fast winds that will blow from the day side to the night side in a sort of a steady state. Yes?
Why do they have to be tidally locked?
Because the tides are really, really strong when you're that. So the planet is actually shaped like a rugby ball, and it really wants to have the long side of the rugby ball facing the star. Yeah, and if you try and come up with any other state, it will dissipate a crap load of energy until it finds that minimum energy state. Yeah, but we're trying to test this empirically. So like I'm telling you this and you're taking it as like just the gospel truth, but rest assured we are observing these planets with the James Webb Space Telescope. One of the things we were looking for is, are they actually tidally locked? Because what I haven't told you is that most of these planets have sibling planets in the same system, and those planets are yanking on your lava planet. So in fact, they can't actually be perfectly tidally locked, but just ignore that for the rest of the talk, because I want to keep this story simple. Okay, so they have an atmosphere. The atmosphere is moving hella fast, but it turns out the atmosphere is basically optically thin. So what that means is that you're sitting on the surface of your lava planet, your star is really big, you can actually see your star. That's what I mean. It's like the light from the star just passes right through that wispy atmosphere made out of rock vapor. Later on, I'll show you what an actual absorption spectrum looks like for silicon monoxide, which is the most common constituent in their atmosphere, SiO. And you'll see that it indeed is basically transparent at visible wavelengths, so you can see right through it. That is not true in the ultraviolet, it's not true in the infrared, but at visible wavelengths, it's see-through. So what that means is that the surface temperature of this planet doesn't care about the winds. Like the winds are literally supersonic. The winds are going at like Mach 15, and if you live on the surface of this planet, you don't care about the winds. What you care about is like how big the star is in your sky. It's very big. So what that means is there's a big chunk. Let's see, can you see my cursor? Does that work? Okay, that kind of works. There's a weird lag that makes me nauseous if I look at it. Okay, so I'm just gonna look at my screen for now. So this part on the left, wait, I think I have animations. Okay, I don't even need my cursor. I've got animations for this. The day side of the planet, this is the part that's fully illuminated. What that means is that you are seeing the full disk of your star, like the entire star. You're seeing the entire thing. There, the temperatures are like 2,500 to 3,000 Kelvin, okay? Then there's a night side over on the, I guess you're right. There's a night side, and again, the equilibrium temperature there is 0 Kelvin. The actual temperature will probably be closer to 50 or 100 Kelvin, or 1,000 Kelvin, as I will get to later. And it's cold, but then there's a really big kind of twilight region. That's the region where you are seeing some of the disk of your star, but not all of it. In other words, seen from that vantage, the sun is like rising or setting, but of course the sun is not moving in the sky because the planet's tidally locked. So if you're at a fixed location on this lava planet, your star is always at the same location, stuck in the same state. The bottom line is that on a planet like this, the day side is a third of the planet. The night side is a third of the planet, and then there's another third of the planet that's in this weird in-between zone. Okay, so there is no like illuminated hemisphere and dark hemisphere like we have on Earth. That works pretty well on Earth because Earth is sufficiently far away from the sun that to good approximation, the sun's rays are coming in parallel. On this star, the sun's rays are not coming in parallel. They're coming in like from different angles, because again, the star is really huge. So there you go. Okay, so this is the basic like illumination pattern. This goes into like all the calculations we do for the atmospheres of these planets because it kind of matters. Okay, so now here's work done by Zhang Wan, who at the time was a graduate student at York University that I was co-supervising with John Moores, and is now a postdoc in my group. So what we're showing here is atmospheric pressure. So the y-axis is atmospheric pressure. It's on a log scale. And on the x-axis is angular distance from the substellar point. So 0 means you're directly underneath the star. And then as you move to the right, you're moving farther and farther from the substellar point. So in principle, the temperature is getting cooler. And because the way saturation vapor pressure works, at cooler temperatures, the atmosphere can hold less vapor. And so the atmospheric pressure drops, right? So this is the same thing, it's the same reason why you're like nosebleeds in the winter, right? Because it's like colder air can hold less moisture, so the air is drier, that kind of thing, right? It's very humid when you go to the tropics because it's hotter, more moisture in the air, right? Same principle, but here the moisture is rock vapor. Okay, so what you see is that it goes like this, and then it just like tanks, right? So the pressure is just like plummeting because what's happening is the entire atmosphere is collapsing as I'm moving towards the night side. So yeah, that's the basic picture. There you go, this is what I just told you. Okay, the pressure is dropping to 0 as you get to the colder parts of the planet. And then if you look at the wind velocities, so this is like a, how to describe this? This is sort of like a custom-built atmospheric dynamics model. So you can't use like a general circulation model or a global climate model. The things people use for like understanding Earth climate will not work on a lava planet because those things are predicated on very reasonable assumptions, like winds don't go faster than the speed of sound. Your atmosphere exists on like 4 pi steradians, like the entire planet. And those assumptions are not correct for lava planets. You have to like kind of make these like bespoke, like one-dimensional fluid dynamics calculations. So this is what my student Zhang did. And here are the results. So the bottom panel is showing the speed in meters per second is the left axis and the Mach number on the right. So you can see that like as you get towards the point where your atmosphere is really wispy and collapsing, the Mach number is getting up to 10, 20, 30. So you're going at like 25 times the speed of sound. Yes?
Can I just ask, when you say Mach number, you're referring to like Earth conditions, speed of sound, rather, or?
No, it's the local Mach number. That's what matters for these simulations. Like the thing that makes these simulations hard is when things go transonic. Like when you cross the speed of sound, it's the same reason why it's like, hard to, have Concorde jets and stuff like that. Like the simulations likewise crap out when you get to the speed of sound. So then you have to be very careful there. So you want to know like how much faster than the speed of sound. And the really high Mach numbers are actually not a problem. The real problem happens right around Mach number 1. Is right when you hit the speed of sound. That's when things are numerically divergent. You have to be very careful about the simulations. Okay, so winds are going fast. So our basic cartoon at this point is something like this. So now I've flipped so that the hot part of the planet is facing down. So the day side is a magma ocean, about 3,000 Kelvin. There's this rock wind blowing towards the night side. As the wind blows towards the night side, it gets cooler and cooler, and at some point it starts condensing out. So you're going to get rock rain and rock snow. And then, of course, you can't just keep removing mass from one part of a planet and dumping it somewhere else. Like, eventually, the planet will be like all imbalanced and non-symmetric, and it's going to like flop over, right? Because you will have done something weird to its moments of inertia. So there has to be a return flow in the steady state, and that return flow is mostly through a magma ocean current. So again, if you put on your like Earth goggles, this isn't that weird. This is like Earth does this shit all the time, right? On Earth, you have evaporation in the tropics. You have Hadley circulation, moves that humidity to places like here, where it snowed last night. And then, what happened to the mass, that we moved? Well, you just have ocean circulation, like the snow will melt, it'll go in the St. Lawrence, go in the Atlantic, the water moves around, it's all fair, right? So this is basically just like a water cycle, just with rock. Okay, so it's not that exotic. One of the things that is weird is that you can calculate how fast these currents would be, and we'd calculate it in a pathetically naive way at the time. We're trying to do better now. But at the time we calculated this, and we convinced ourselves that the return flow, which is going to be governed mostly by your silicates, SiO, SiO2, things like that, that return flow is actually too slow to replenish your sodium and potassium in the atmosphere. So essentially the magma pool at the substellar point, the hot place that's generating your atmosphere, might be depleted in sodium and potassium. Why the hell would you care about this? Because sodium and potassium are really easy to detect astronomically. So when we look at a distant exoplanet, like the very first thing we ever detected on an exoplanet was sodium. It was Na, right? That was it was like Charbonneau 2002, right? So this is like, it's easy to detect. And so it's important for us to know as astronomers, like, do we expect to see sodium and potassium? And our prediction as of 2020 was like, well, maybe not. Maybe we won't see sodium. Where does it get stuck? It gets stuck in these weird ice sheet kind of glacier things beyond the shore of the magma ocean, which is fun. So it's kind of like an alkali glacier-ish. Okay, so that's the basic picture. I think that basic picture is roughly correct. Now let's get into some kind of like higher order details, and some of the details actually matter. So radiative transfer. So I basically told you that the atmosphere is transparent. And so everything I've done so far is fluid dynamics, thermodynamics, but there's no radiative transfer. I basically don't care about the photons. Like the photons come in, they dump their energy at the surface of the planet. That dictates the temperature. The temperature dictates the vapor pressure, and then the vapor pressure dictates the fluid dynamics. But it's a little bit more fun than that. So here on top is a spectrum of silicon monoxide, so SiO, so that's a spectrum of it. Again, notice the y-axis is a log scale. So optical wavelengths are sort of in the middle, like half a micron. And at optical wavelengths, the numbers are really small, 10 to the minus 34 in case you can't see that. So the point is, it is transparent at visible wavelengths. But if you go either to the right, to the infrared, you see that there's actually more absorption features, right? So these are basically rotational vibrational modes, right? So it's silicon monoxide. It's like a greenhouse gas, right? It's like carbon monoxide or water or methane or something, right? So it can absorb infrared radiation. But then if you go into the ultraviolet, it's also really good at absorbing ultraviolet. So that has some consequences. Because if you look at the stellar spectra, which are in the bottom, mostly they basically look like sun-like stars. But the point is there's slight differences. And those very slight differences between those colored lines in the bottom panel, those are the host stars of specific lava planets. And those very minute differences make a big difference in terms of like what their atmospheric dynamics and things are like. Because it basically determines how much ultraviolet light is going to come into the atmosphere. Okay, and the ultraviolet light is critically important, and it leads to like a very weird feedback. So again, the atmosphere is, you get less and less atmosphere as you move away from the substellar point, so you're getting towards the dark side of the planet, and the atmospheric pressure is dropping. Interestingly, and this is what the bottom panel is showing, if you look at the temperature of that gas, the atmosphere is actually staying at pretty much the same temperature all the way until it collapses. And the reason for that is this very weird phenomena. It's a balance between ultraviolet heating, which is not so weird, and ultraviolet cooling, which is kind of weird for a planet. Usually planets are not hot enough to radiate in the ultraviolet, but on lava planets they are. That you just get like the little tip of your Wien tail on your Planck function starts actually peeking into the ultraviolet. So what's happening here is that you have a balance between UV heating and UV cooling that maintains the atmosphere to just like stupidly hot, like around 3,000 Kelvin all the way until there is no atmosphere anymore. So even though you would expect the atmosphere to be cooling as you move away from the substellar point, it actually stays at basically the same temperature the whole way. And so this was fun. So this was like our first hint that like, okay, maybe radiative transfer actually kind of matters. Again, at most wavelengths, we don't see the atmosphere. When we look at these objects, we will see the surface. But this atmosphere is made out of silicon monoxide, and silicon monoxide, as I showed here, has absorption features in the infrared, which means we can actually see them with the James Webb Space Telescope, which means if we look at the right wavelengths, we can look at the atmosphere, see what the atmosphere is doing, and then we go to a neighboring wavelength, and now we see through the atmosphere and we look down at the surface. So it's the same game people do, if you look at Earth's atmosphere, you can look at like the emitting temperature of the Earth, and it's the same game, right? If you look in a carbon dioxide band, then you are probing the upper atmosphere, and then if you go off of that band in some place where the atmosphere is transparent, then you're seeing more or less the surface temperature of the Earth. Okay, so no questions. That's good. All right, this is too small. Yeah, this is way too small. I can't read it on this. Can you guys? Probably nobody can read it. Let me tell you the punchline. Oh yeah, this is horrible. Sorry. This is an example of what happens the first time you give a talk. You realize some of your slides were a bad idea. I'll tell you the two punchlines of this. Just listen to my words. Don't stare at the screen. The two punchlines are the precipitation rates, right? So if I have an atmosphere that's collapsing, I mean, that's not, that means that there's like actually drops of silicate, like rock, and snowflakes silicate flakes forming, dust grains, if you will, that are falling down. So it's precipitation of some kind. The precipitation rates, oh man, it's 0.5 meters per day. Okay, so to put that in perspective, that'd be like a pretty badass snowstorm, right? That's just the steady state. So it's like a snowstorm of just like rock snow, just like snowing down on the planet. So that's cool already, just because you're like, wow, that's weird. And one of the things that we've been starting to think about and trying to implement is what impact would that huge amount of precipitation have on the magma ocean circulation? But I realize I haven't told you about the magma ocean circulation yet, so you don't fully appreciate how cool that is. But the other thing that's good to point out is that if you have all this precipitation, that means there's probably clouds. I mean, I kind of hinted at this when I had that goofy cartoon with like the cartoon clouds, right? And I said, oh, look, it rains and snows rocks. But like, if you have clouds made out of silicate, like that will actually reflect away some sunlight from this planet, and that should change the underlying temperature. Okay, so this is a place where radiative transfer matters, right? When I have silicate vapor, it is see-through. Sunlight basically passes through it unmolested. But when I condense it into clouds, now it interacts with the atmosphere. Again, anyone who studies the Earth is like, obviously, because that's what water vapor does, right? Like water vapor is like see-through. And then when you condense it, you make clouds, and suddenly those interact very importantly with incoming and outgoing radiation. So the same thing happens on these planets, and this is one of these things where poor Zhang worked really hard on this, and the punchline is it doesn't actually change the big picture of like the atmospheric dynamics of these planets. Like we thought it was going to lead to some sort of catastrophic like collapse of the atmosphere or something wacky, and like not really. So the dynamics that I told you before basically work. It's just that now you have to picture there actually are clouds, and the clouds do slightly cool the temperatures, but not enough to change the big picture. Yes?
How does the temperature of the atmosphere being uniform, how does that affect the precipitation? Because you think that the precipitation would be caused by it cooling down.
Yeah. Yes, this is a great question. I'd have to dig through Zhang's paper, which is currently to try and remind myself like how much of a difference it makes. But the thing is that your intuition is correct, but that's because on Earth you're used to pressures not varying that much when you move around, right? So, but in this case, as your parcel of gas is moving along towards the night side, which I guess is this way on all the diagrams I've shown you, the pressure is dropping by orders of magnitude. So the change in pressure is more important than the change in temperature in terms of where you cross the condensation curve. But it's, yeah, it all is sort of self-consistently accounted for in the simulation. Yeah.
What would the height of the atmosphere be?
Like the atmospheric scale height?
Yeah.
Yeah, it's not that different from the Earth. I mean, it's a lot hotter, right? So, and the scale height is proportional to temperature, but the mean molecular mass is higher because it's like silicon monoxide instead of like N2 or O2. So it ends up being a higher atmospheric scale height than the Earth, but not like dramatically so. So like, tens of kilometers kind of thing. Yeah, so it makes it very hard to do transit spectroscopy. For those of you who know what transit spectroscopy is, not good targets for transit spectroscopy. Okay, I'm going to leave this plot because I found it offensive. It was just like, it was making my eyes bleed just trying to look at it. Okay, so next question is, how deep is the magma ocean on these planets? So I hopefully convinced you at the beginning that there has to be some liquid magma at the surface of this object, but how deep is it? Is it a puddle? Is it as deep as our ocean? Is it like all the way down? Let's see. So, okay, this is for the non-geoscientists in the room. So this is important things that physicists don't always know about the Earth. Newsflash, the inside of the Earth is hot, and yet it is solid. Most of it is solid, okay? And that's just because of the way these phase diagrams go, because the pressure is high down there, okay? So the temperatures get high, but it's still solid, and solid in this is green. Don't ask me why. It's just that at some point early on in this project, we settled on green, and we just stuck with it. So it's solid rock all the way down, okay? So this is kind of what Earth looks like. But, as I was saying before, we know that Earth started hot. We know all these planets start hot. Why? Because if you take two halves of the Earth that start at infinity, at rest, and they convert that gravitational potential energy into kinetic energy, now they're going really fast when they hit each other. And what are they going to do? Are they going to make a loud sound? No, because you can't propagate sound in space, right? So what do? You just get really hot. So you convert all that kinetic energy into thermal energy, and then you radiate it away. So that's what normal planets do. And of course, on a lava planet, you can't radiate away your energy quite as efficiently because you're being bombarded with more radiation from your star. So the punchline is that if Earth's core is still hot, which it is, then the core of a lava planet must be at least as hot. Okay, this is not rocket science. This is just like basic intuition. Okay, so now we try to do this a little bit more carefully. So this is work done by Charles-Édouard Boucaré, who goes by Shed. He's now a prof at York University. This is one of like the amazing happy things that happened with COVID. COVID was mostly just bad, but Shed is French. He was supposed to be working in Paris at the time. He was a postdoc in Paris, but his girlfriend is French-Canadian, so he was living in Montreal, and I heard about this during the pandemic, and we would like have these like conversations across a picnic table from each other. And he studies magma oceans like for the Earth and the Moon and trying to understand like solar system formation. And when I told him about lava planets, he was like, that's so cool. He's like, yeah, let's do lava planets. So we collaborated, and now we're still doing some fun collaborations thinking about lava planets. Okay, so this is a phase diagram. This is like the phase diagrams you are familiar with, except probably if you're a physicist, you're not used to this partially molten thing. So that's basically because you're used to thinking like water or like a pure substance, you know? But a mineral, you know, rocks are more complex. They're not just like a single element. And so you get this partially molten part, which is called mush. That's the actual name. If you're not familiar with this, you can think of it as slush. Okay, it's this kind of like weird thing that's not quite liquid, but not quite solid. Okay, so this is important because if you start plotting plausible geotherms, this is basically like what does the temperature look like as I drill down on my lava planet. Okay, so the surface is at the top of this diagram and I'm going down. And so these lines, the lines going down are basically adiabats for people who are used to thinking about that. You know, so it's basically like if I have something, if I have a parcel of magma and I move it up, and it's going to, you know, the pressure is going to decrease and it's going to do PDV work and it's going to cool down, right? So this is the same thing that dictates the temperature profile in our atmosphere, right? This is why it gets colder as you go up. This is why it's cold on top of mountains and stuff, is you're just following an adiabat. So it's the same principle as you go down into a magma ocean. In that case, you're going down and the pressures are going higher, which means the temperatures are going up. And basically, the point is the temperatures are going to increase, and for reasonable surface temperatures, like 3,000 Kelvin, which is like at the substellar point on a lava planet, that adiabat, here, let me see if I can do the cursor trick, that adiabat there is staying in the liquid part. Remember, that was the molten, that means liquid part. It's staying in the liquid part all the way down off the chart. Okay, which means it's actually plausible that at the substellar point, this planet is molten not just in a puddle, not a kilometer deep, not 100 kilometers, not 1,000 kilometers, but thousands and thousands of kilometers, all the way down to the core. Okay, it's just molten the whole way down. All right, so then you get a cartoon like this. Okay, so the day side is fully liquid, all the way down to the core, and the night side may be fully solid, and then in between you have this mush. Okay, that's kind of like a mix. Blah, 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 blah. Okay, the mush is near the terminator. Okay, so the mush is in this kind of the zone where your star is like kind of setting or rising, if you will. It's on the horizon. The mush is important because what happens in a mush is that if I take like a molten piece of rock and I let it cool to the point where crystals start forming, certain things will preferentially go into the crystals and other elements will preferentially not want to go into the crystals. They'll want to stay in the melt. And so the things you think of as being volatile, like your water or even your sodium or your potassium, will preferentially not want to crystallize. They will get more and more concentrated in your melt, which means that as you go closer and closer to the point where your magma ocean is frozen, its composition of the melt, of the molten part, is actually changing. And remember, it's the molten part of your ocean that dictates the atmospheric composition, which means the atmospheric composition is becoming more and more volatile rich as I go towards the terminator, which is kind of cool because if you think about this as an exoplanet like observer person, you're like, well, the terminator of the planet is the part I see when I look at them in a transit spectrum, which means I'm pumping out volatiles right in the region that I might probe with transit spectroscopy. Except that transit spectroscopy is like really hard for these planets. So this is like not a science case for now, it's a science case for like extremely large telescopes. Okay. I think I just told you this. Boom. what are the dynamics of magma oceans, right? So they've got this magma ocean, it's really deep. What is it, how does it move? Here are simulations done by Daphne, who's a collaborator of Shed and I's. She's junior faculty in Scotland, St. Andrews. She's like an applied mathematician. And so we dragged her into this. She usually does Jupiter, the interior of Jupiter. And we're like, come on, come do lava planets, it's fun. So she did some simulations, some three-dimensional simulations of lava planets. What we were really interested in was whether Coriolis forces might matter on these planets. Answer, probably not. But it comes close. Like the viscosity of this magma is very, very low. It is very liquid. It is like as liquid as water, kind of liquid, right? So it is actually pretty, like the convection you get here is actually pretty turbulent. And in principle, Coriolis forces in some edge cases might matter. But the basic circulation you have is upwelling at the substellar point, which is on your left, at least maintained that. So you have upwelling, and then you have a kind of a surface flowing away from the substellar point, so similar to the atmosphere, right? And then as you get towards the antistellar point where it's cold, you'll subside. So again, if you think about ocean circulation on Earth, nothing particularly weird about this. You know, you have downwelling in the North Atlantic that fills like the abyss with cold water, blah, blah, blah. Okay? So Daphne can do these really cool 3D simulations, including Coriolis forces. That's the good thing. Bad news is that she can only do a fully fluid interior. She can't deal with a partially molten mush. So this is where Shed's model comes in. So he's got his own special model. He's got one fewer dimensions. He can only do two-dimensional simulations, but he can account for the partially molten interiors of these planets. So this is what he shows in, this is like a snapshot of one of his simulations, and he actually sees the same basic circulation. I'm not showing the flow lines on this, but I think I do maybe in a later plot. It's the same basic idea. On the day side, you have upwelling, and then you have on the surface, you're flowing towards the night side, and then when you get to the cold night side, as you cool down, your magma becomes denser, and it sinks to the bottom. All right? And so that basic picture still holds, even in this case where you have like a mix of solid and liquids in the atmosphere, not the atmosphere, in the interior. You can tell I usually study atmospheres. Okay, the cool thing with being able to do the partially molten simulations that Shed does is he can actually look at weird things like segregation of metals, okay? So that's what's happening here. So the time axis is sort of going from the top to the bottom. So at the beginning of the simulation, the planet is well mixed, it's hot, everything is basically what we would call a bulk silicate Earth. That's if you take the rocks on Earth, you stick them in a blender, and then you turn up the heat, and you melt it all. That's what the interior of this planet starts off as. That's our initial condition. And then as time goes on, it eventually does actually solidify. You get a very thin magma ocean that's only like, tens of kilometers deep. And what you end up, maybe the weirdest thing, which you might not, so the thin ocean is that little white layer there. That's like a kind of a magma puddle, but like deeper than our oceans. And down at the bottom here, this gray stuff, this is super interesting for the geologists in the room. What that is that's this kind of sludge of iron oxide. So basically all the iron oxide, which is usually mixed in your rocks, is now segregating, and it's just accumulating as a solid at the bottom of your magma ocean. So if this happens over geological timescales, that means that you're going to run out of iron in your atmosphere, which means, again, if you look at this planet with a spectrograph like James Webb, you'll find silicon monoxide, but you might not find iron or iron oxides. So that's a testable prediction. So in cartoon form, where again, orange is molten, green is solid, if the planet still has a pretty hot interior, you're going to have a scenario like this, where you have your magma ocean on your day side is representative of the entire planet. It's basically bulk silicate Earth, which means the atmosphere is going to be the same thing we've been naively predicting for over a decade. The night side is quite interesting in this case. If the planet has a global magma ocean, you can actually transport enough heat to the night side to keep it molten. So it's a bit of a chicken and egg thing. Like you need a magma ocean to transport heat to the night side to maintain the global magma ocean. But at the very surface of that night side magma ocean, you're going to inevitably get a crust. Why? Because you're facing the darkness of space. It's very easy to radiatively cool to space, which means you're going to form this crust. Problem is that crust is going to sink. That crust is actually denser than the underlying magma ocean. Okay? That's because your intuition based on water is crap, because water is the weirdest thing in the universe, right? Because water has this low density form of ice that floats, but other materials don't do that, right? So this magma ocean, when it solidifies at the top and makes this crust, that crust is going to flounder and it's going to sink, which means you're going to be constantly reforming a new crust, and that means the night side of this planet, seen from space, would actually look kind of hot. It would look warm. So we could detect that with James Webb, we think, we hope. The other scenario, and this is sort of like the end game eventually, all lava planets probably look something like this, is you end up with this very thin surface magma ocean on the day side. Night side is like rock solid, it is cold. But that day side magma ocean now is very chemically evolved. It is no longer representative of a bulk silicate Earth. It is now some weird, like distilled version of rock, where you've removed certain elements. You might have removed your alkalis to some glacier on the night side. You might have removed your iron to some sludge at the bottom. And so now you have this kind of weird evolved kind of chemistry. Could we detect this? Probably not. Probably not unless someone gives us a lot of James Webb time, but we'll try. If you serve on a James Webb allocation committee, remember this favorably. It's hard, but yeah, it's no harder than trying to search for signs of atmospheres on planets that are probably airless rocks, which a lot of my colleagues are doing. In fact, I'm doing sometimes too. Okay, how long can the magma ocean last? Okay, this is sort of the next level question. This is Mahesh. He's a PhD student that Charles-Edouard Bouccaré and I are co-supervising. And he's actually trying to make kind of like a box model of how heat percolates out of a lava planet. And I'll skip over I mean, basically there's these layers that we've already discussed. At the bottom, you got the core, you got solid rock. Above that, you got a mush layer. And then above that, you got a liquid layer. And then as time goes on, the solid layer gets thicker, the mush layer gets thicker, and so forth. And eventually, in the steady state, you end up with, something like the cartoons I was showing on the previous slide. But this is trying to do this more quantitatively over the lifetime of a planet. So this is an example of one of these simulations. I won't go into the details of what all these lines mean. But the point is we track like all these different points in the atmosphere, not in the atmosphere, in the interior, and we track how their temperature evolves over time. And then this is maybe the key takeaway, is that we can look at the day side and the night side of a planet, and you can see what happens, right? So on the day side, which is again on the left, you can see that as time goes on, when your planet is quite young, like 1,000 to 10,000 years old, your magma ocean will actually get quite thin, and then it'll stabilize at 1,000 kilometers deep or so. But underneath that, you don't have a hard surface. Underneath that, you have mush, okay? Which means that it's really, the boundary of this magma ocean is actually a little bit weird, okay? Because the bottom of it is just like really thick mush, and there's only towards the end you start getting actual solid rock above your core. On the night side, on the other hand, things cool off pretty quickly. And so you end up with mush for a long time, and then after about 1 billion years, you have solid rock on the night side. So it still takes a long time for this planet to cool. But if you turn on magma heat transport, so this is like now you account for the fact that the magma ocean is actually advecting heat from the day side to the night side, then you get this scenario down here. And it's kind of hard to see, but there's a magma layer that persists at the top. So you have this thin magma layer that might be hundreds of kilometers deep, and it just persists in the steady state. Okay? So you're just transporting a very small fraction of the day side energy that gets absorbed, and through the magma ocean, you're transporting it to the night side, and you keep it from freezing over. Yes?
So if you're sequestering sodium and potassium on the night side, have you accounted for plagioclase flotation?
No. No. Let's talk about that offline. That sounded like an SAT word, so yeah. It's a word I've heard before, but I have no idea what it means in this context. Yeah, okay. Yeah, got it. Okay, no, yeah, we should talk about this. Yeah, it's an interesting idea. Yeah, in fact, Shed and I, this is sort of it's the latest frontier, is we're trying to figure out the physics of this thin crust and its floundering versus not into the ocean. And so this sounds interesting. Okay, so the point is, if you can transport some heat from the day side to the night side, you can maintain a magma ocean on the night side in perpetuity. So obviously in this case, there would be no glaciers of alkalis on the night side. Like in this case, the entire magma ocean would be pretty homogenized. Okay, last but not least, observations. Like I said, there won't be much to say about observations, but I'll show you what we've got. There's basically 3 tricks we use to try and study exoplanet atmospheres on short period orbits. I'm only going to talk about 2 of them. Eclipse is when a planet passes behind a star. Not to be confused with the eclipse that you're all going to see in like a month or 2 when the moon will pass in front of the sun. And so if we make eclipse measurements, basically what they tell us is like, yeah, the day side of the planet is stupid hot as we expected. So there's nothing super surprising there. The more interesting thing is we can look at the phase curve. So now we can observe the planet for a full orbit, which remember, this planet is going around its star every 6 hours, so you don't have to wait very long to get these kinds of measurements. In practice, you stack many, many orbits of the planet to try and build up the data. So we did this, and basically we could just maybe tease out some phase variations, which told us that the night side was cold-ish. Like, at least the night side is much colder than the day side, but that doesn't tell us much. Like, so we can't tell whether the night side is 1,000 Kelvin or 100 Kelvin. Fortunately, we have James Webb Space Telescope observations, which will do much better. The data I just showed you are from the Spitzer Space Telescope, which is small. The James Webb Space Telescope is huge. It's much more performant. And so there were 2 observations of this same system that were taken with 2 different instruments. Yeah, so keep your eyes peeled for those. We're still analyzing them. Okay. Summarizing, so what we know so far, lava planets, well, A, they exist, which is kind of cool. B, they must have magma oceans, which means they must have silicon monoxide atmospheres, because magma is mostly like silicon monoxide. Like you can't have one without the other. They're going to have supersonic winds. Their atmosphere is almost certainly going to collapse on the night side. And the depth and extent of the magma ocean depends on things that we don't fully understand, so it'll basically depend on the interior temperature of the planet. That's sort of like one of the knobs we're playing around with because we don't know how hot the insides of these planets should be. In some cases, we don't even know how old these planets are. Some of them seem to be orbiting young stars, like less than 1 billion years old. Some of them orbit older stars, like more like 12 billion years old. And the presence of your alkalis or iron is going to depend on these sorts of distillation processes, either forming ice sheets, losing things to space, which I've completely ignored, but I'm interested in, or getting things stuck at the bottom of your magma ocean. The day sides are hot and the night sides are cooler. So I color-coded this. Purple stuff is kind of what we know in theory, and orange-red stuff is stuff that we've actually verified with data. So what we're working on now on the theory side is we're trying to couple the atmospheric dynamics and the ocean dynamics. This is a fun project. We're trying to actually look into these weird alkali glaciers and the physics of those. And we're trying to couple the orbital evolution of these planets because they can't have formed where we see them today. We know they must have migrated there. So we're trying to couple their orbital evolution to their interior thermal evolution. Because as the planet migrates, it undergoes tidal forcing, which should warm its interior, melt it, do some interesting things. And on the observational front, what we're working on is we're actually trying to measure their night side temperatures. We want to measure like how hot are they for real? Like are they 100 Kelvin, are they 200 Kelvin, 800 Kelvin? We want to know how warm that night side is because that'll tell us what's going on underneath the surface. We're trying to actually measure silicon monoxide. I keep saying that it should have silicon monoxide. If that's true, we should eventually detect silicon monoxide because it has spectral features in the infrared. And what we want to know is, does the temperature go up in the atmosphere or does the temperature go down in the atmosphere? So it's like, is the temperature inverted or not? This will ultimately tell us basically indirectly about sodium and potassium because sodium and potassium are good ways to get a temperature inversion. It's sort of, they play the same role as like ozone does in Earth's atmosphere. Ozone gives us a temperature inversion, so it's the same game. And we want to actually look directly for sodium, potassium, iron. Those things all have spectroscopic features that on a good day, if we can't do it with James Webb, we'll definitely be able to do it with the next telescope that someone gives us time on. And with that, I think I'm out of slides. Thank you.